This video is part of the Commercial Building Electrical Design series. We're dealing with lighting design, and we're starting with lighting terms and definitions. So just to take note of where we are just now beginning the lighting design portion of this video series. So we'll now begin our look at lighting design, which is much different than power design. It's different in a couple of ways. The first difference is that while power design has some very strict guidelines and requirements defined by the NEC, lighting design has no such requirements, with the possible exception of egress lighting. In fact, there really is no requirement for lights at all. A client could put candle holders in their building if they like. Lighting design is very subjective in that it can vary greatly depending upon who the observer or client is. This can present some great challenges when doing lighting design. Before we can dive too far into lighting design discussions, we first need to define some terms and concepts that will be used to evaluate and characterize lighting. Once we have the proper terms defined, we can then use these concepts to evaluate different types of lighting. We can also compare how these different types of lighting perform in different applications and environments. So light itself is the radiant energy in the electromagnetic spectrum, which can be sensed by the human eye, and it's measured in lumens. And so if we look at a graph of the electromagnetic spectrum, and this goes all the way from radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma rays, you can see the associated wavelengths from pretty large waves all the way down to very small or short waves. You can see that it's just this area right here that light becomes visible to the human eye. So it's between 700 nanometers and 400 nanometers in wavelength. And so the rest of these wavelengths can't be detected by the human eye. And it's probably a good thing, because if we could see all these frequencies, we likely would have a very hard time seeing it all. It'd probably be like you're blind, because you'd just be washed out all the time. Your rods and cones would be firing nonstop. One thing that is important to think about, when you see something, you don't actually per se see the target or the item. You see the light reflecting off of the item. So that's something that's very important, and we'll talk about that more as we go look at lighting design and how things are perceived. So looking at some definitions, the electromagnetic spectrum, which we just saw a graph of, that's a continuum of electric and magnetic radiation that can be characterized by a wavelength or frequency. Visible light encompasses a very small part of the electromagnetic spectrum in the region from about 989 nanometers, which is violet, all the way down to 770 nanometers, which is red by wavelength. So again, referring back to the graph we just saw, that pretty much correlates with what we saw there. Just for reference, a nanometer, so this is a unit of wavelength, and it's equal to 10 to the minus 9 meters, so very small. One spectrum, part of the spectrum that is of importance to us that we really don't see is the wavelength range from about 1 millimeter to 700 nanometers, and this is the infrared region. So energy in this range, again, can't be seen by the human eye, but you can sense it with the skin as heat. So we use this for heat. Another part of the spectrum is the ultraviolet region. So radiant energy in this range is about 100 to 380 nanometers. So for practical applications, the UV band is broken down into other bands, and those are ozone producing, which is from 180 to 220 nanometers. The bacterial or germicide region, which is 220 to 300. The I'm not sure how to pronounce that, or erythermal, skin reddening, 280 to about 320, black light, which is from about 320 to 400. The Internal Commission on Illumination defines the UV band as UVA, UVB, and UVC. And you can see the corresponding wavelengths there. So you may be familiar with a device that's used at like the dentist office, such as an autoclave. It uses UV radiation to sterilize instruments, and so it usually has a UV bulb in there somewhere in the 220 to 300 nanometer range. So we now want to examine some terminology used to quantify or describe light in measurable terms. So the first one is a lumen. So this is the international unit or SI unit of luminous flux or quantity of light. For example, a dinner candle provides about 12 lumens. A common 60-watt incandescent lamp, if you can still find those, that gives us about 840 lumens. So just to give you some frame of reference there. We next have a term lumens per watt. And so this is a measure of the efficiency, or more properly, the efficacy of a light source. So efficacy is easily calculated by taking the lumen output of a lamp and dividing by the lamp watts. For example, a 100-watt lamp producing 1,750 lumens has an efficacy of 17.5 lumens per watt. So just by comparison, we'll get into the details of some of these different other lamp types. You may be familiar with some of them, but Edison's first lamp had an efficacy of about 1.4. Incandescent lamps are from 10 to 40. Fluorescent lamps, which you've probably seen those, anywhere from 35 to 100. And then high pressure sodium lamps, 100 to 140. Of course, the new kid on the block, which is they aren't as new as they used to be, is the LED bulbs or LED lights. They have an efficacy of 140 to 300. So this is one of the reasons why they are kind of taking over the market and have been for a while, because they are just so efficient that it doesn't make sense to use any of these others when you can use the LED bulbs. Another term is candela. So this international unit of luminous intensity is a term that has been retained from early days of lighting, when a standard candle of a fixed size and composition was used as a basis for evaluating the intensity of other light sources. The unit's rarely used in lighting design anymore. However, it is still regularly used in describing fire alarm strobes. So when we get into fire alarm design, you'll see this term pop back up for candela rating. Candle power, so luminous intensity expressed in candelas. Plots of luminous intensity called candle power distribution curves are used to indicate the intensity distribution characteristics of a reflector or a type of lamp. Lux, again, this is another SI unit of illuminance. 1 lux is equal to 1 lumen per square meter. Foot candle, this is a unit of illuminance or light falling onto a surface. 1 foot candle is equal to 1 lumen per square foot. So this is the one that we use the most when we're evaluating lighting performance in a room and using it to design. You can use lux if you want. They're comparable, whereas this is 1 lumen per square meter, 1 lumen per square foot. If you want to go back and forth, the factor is about 10. So 1 lux is equal to about 10 foot candles, if you want to go back and forth on that. Luminance. So formerly a measure of photometric brightness, luminance has a rather complicated mathematical definition involving the intensity and direction of light. It should be expressed in candelas per square inch or candelas per square meter, although an older unit associated with this is foot Lambert. This is still sometimes used. Luminance is a measurable quantity, whereas brightness is a subjective sensation. So whereas they used to use this to describe brightness, now we've come to realize that brightness can be subjective. So what we're trying to measure then is the intensity and the direction of the light. A related term is illuminance. So this is the density of light, lumens per area, incident on a surface. Illuminance is measured in foot candles or lux. So the difference between luminance and illuminance. Luminance has to do with the source, how much light is leaving the source. Illuminance has to do with how much light is hitting your target and, at that point being reflected back or illuminating your target. So color temperature, which this definition's been expanded to correlated color temperature. Originally a term used to describe the whiteness of incandescent lamp lights, color temperature is directly related to the physical temperature of the filament in incandescent lamps. So Kelvin, which is the absolute temperature scale, is used to describe the color and temperature. So for discharge lamps where no hot filament is involved, the term correlated color temperature is used to indicate that the light appears as if the discharge lamp is operating at a given color temperature. More recently, the term chromaticity has been used in place of color temperature. Chromaticity is expressed either in Kelvin or as an X and Y coordinate on the CIE standard chromaticity diagram. A higher color temperature describes a visually cooler, bluer light source. Typically, color temperatures are 2800 K for incandescent, 3000 for halogen, 4100 for cool white fluorescent, and 50,000 or higher for daylight and simulating fluorescence. So what happened was, we had these filament bulbs like Edison created, or the incandescent bulbs, and the more you would turn up the voltage and make the filament hotter and hotter, the color would change and get whiter and whiter. And so they realized that they could describe, what color they would get by what temperature the filament would be at. So that's where we get color temperature from. So here's an example using LEDs. LEDs, we can virtually achieve any color temperature we want by programming it or using the right semiconductor mixture on it. So here you can see 2700 is a little more yellowish, and then it gets whiter and whiter until you get up to 5700K, 7000K. This is a really white type of light. And so it correlates over here in this color band, where we hit here. See, like we said, moving more toward the bluish region of the color spectrum. I wanted to take a quick look at the chromaticity chart that we mentioned. So this is the chromaticity chart. And so this is the original color temperature range here, going from red to the bluish region. And so when we had a filament, this is all we had. But then we realized as we started getting different types of bulbs, all the way up to, and especially LEDs, we could get colors off this line, so we could get them anywhere in this region. So that's why we went from the color temperature linear range to the chromaticity two-dimensional range. So this is why you can get a coordinate, XY coordinate, to describe the color of a light bulb. Some other terms you might hear in relation to that in temperature used to be warm, white, neutral, cool, and daylight. And so again, these are just moving up the temperature scale. And they used to use these terms to describe light bulbs. So you could say you wanted a cool fluorescent, or you wanted a warm incandescent. And it's not a huge difference here, but as you go across this, you can see it goes more from a reddish, a little bit of a reddish hue to almost a kind of a sterile white over here. So that's why we kind of try to live in this region in business applications, and then we try to stay in this region for residential looking areas. One other quick chart that I found I thought was pretty interesting. This goes all the way down to 1800K, where you can see this is really red or orange here. This is using just a standard white environment or test subject. So you can see as we go up, it starts to get whiter and whiter. And again, when you get to 5400K and above, it really washes out there. So another thing we need to be aware of is color rendering index. You'll see this abbreviated as CRI. So this is an international system used to rate a lamp's ability to render objects' colors. So the higher the CRI, based on a 0 to 100 scale, the better colors appear. CR ratings of various lamps may be compared, but a numerical comparison is only valid if the lamps are also rated for the same chromaticity, that is, color temperature. If you start comparing two different color temperatured bulbs, then it's hard to relate the CRI value. So CR differences among lamps are not usually significant, that is visible to the eye, unless the difference is more than 3 to 5 points. And so we'll look at an example of that. Here's a table that was put out by a lighting manufacturer years ago that I thought was pretty descriptive. So here they're showing the difference in their different types of bulbs. So they had a standard bulb, a good color bulb, and then a very good color bulb. So that way they rated them. They were SP or SPX, I believe. And so here you can see that the CRI, which is in the parentheses here, so it's 50, 60, 49. Here it's 78 all the way across, and here it's 86 all the way across. And so you can see how this varies as we use different temperatures. So here we can compare the same temperature. So these two are about the same color temperature here, and you go from a 49 to an 86. You can see the colors are rendered much better here than here. Same thing with here. If we come down in this temperature range, 52 compared to an 86 here, looks much better here. So I thought this was a pretty descriptive graph to kind of show how it is. So it's almost impossible to compare here to these two because the color temperature, like they said, is different. So it's kind of an interesting little graph to show how that works. So another concept we need to be aware of is the spectral power distribution. So a graph of the radiant power emitted by a light source is a function of wavelength. That's what this is. So SPDs provide a visual profile or fingerprint of the color characteristics of the source throughout the visible part of the spectrum. So while CCT and CRI are useful measures to indicate the color of a light source, the true and complete information about the source is contained in the spectral output curve. So let's take a look at what this looks like. So these curves tell how much energy the lamp is emitting in each region of the spectrum. So for example, the incandescent lamp spectrum, the top one, shows almost no blue colors. So being that being that what we see is the light reflected from a target, if your target had a lot of blue in it and you illuminated it with this bulb, you're going to have trouble recognizing the blue. It's probably going to come back more of a gray color. Whereas if you were to use this fluorescent, you can see the fluorescent does have some representation in the blue, has a lot in the green, the yellow, and the red. So this one's probably going to do pretty well with any color, but it would catch blue. You come down to a metal halide bulb, you can see here that they do have at least some representation all the way across. So you could illuminate something blue here. But if you're wanting red, then incandescent could possibly outperform these two, depending on what color you're looking for. So here's a graph kind of comparing some of the major bulb types. Of course, the interesting one is sunlight. Sunlight has all of the wavelengths just very well represented. So that's why outside in the daylight, if you're trying to tell what the color of something is, that's the best place to go look and see. Go outside and look in the sunlight. But if you use LED, we can get just about any color in the LED spectrum. There's a little bit of a challenge between the dark blues and the light green area and bluish green, but for the most part we can capture it. As we showed before, incandescent is going to really struggle on the blue side of things, but perform pretty well everywhere else. Fluorescent, which is CFL, stands for compact fluorescent. It also does pretty well. It doesn't do quite as well up in the red region, but you're going to do pretty good in all the other regions here. And here's your corresponding wavelengths across the bottom here. So taking these all into account, this is what makes for issues, just like the uh, the thing that went viral a few years back about which color is the dress, and there's been various ones since then, and some of it just has to do with how things are rendered and what environment you're in when you're trying to look at them and see what's going on. So just some interesting things to keep in mind as you want to start thinking about lighting design, because it's important. What are you lighting? What are the colors I want? What kind of performance do I need? And those types of things.